We move on to another type of collision of great importance, which is the glancing collisions. Like in billiard ball collisions, if the collision was head-on, that would be a simple elastic collision like the one we just discussed. But if the collision was a glancing collision, as you can see here, then after collision, the first ball will move in one direction and the other ball will move in another direction. So this problem is a collision in two dimensions. That's to say, you need to conserve momentum along x, and also you need to conserve momentum along y. So before collision, momentum along y is 0, momentum is all along x. This means after collision, the momentum along y must also be 0. So if you decompose this velocity and decompose this velocity, you write the momentum here and the momentum here. They should cancel each other, such that momentum after collision along y is equal to momentum before collision along y. Then you decompose this vector to horizontal components, and these two components of the momenta, when you add them, should equal to the available momentum before the collision. So for the x component, we have this equation. So here m1 v1 cosine theta, and for m2 v2 cosine phi, another angle here. And for the y component, m1 v1 sine theta plus m2 v2 sine phi. Okay, this is equals to 0. So you can apply algebra, and usually since you have two equations, you can solve for two unknowns. The same strategy that we talked about earlier, you can always apply it. You need to draw your coordinate system and then to apply the conservation of momentum and the conservation of energy if elastic. If not elastic, skip. That does not apply. I selected this example for the inelastic collisions. A car with mass 1500 kilogram traveling east at a speed of 25 meters per second, this car here, collides at an intersection with a 2500 kilogram pickup truck traveling north at a speed of 20 meters per second. Find the magnitude and direction of the velocity of the wreckage immediately after the collision, assuming that the vehicles undergo a perfectly inelastic collision. That is, they stick together, and assuming that friction between the vehicle and the road can be neglected. So now we need to conserve momentum along x and the momentum along y, since this is two-dimensional problem. So along x, originally we have just this vehicle, so it is mass multiplied by velocity. That is before collision. After collision, you have the two masses together multiplied by the velocity v final multiplied by cosine theta to get the x component. So we have this equation. Okay, this is for x initial, this is for x final. So we have two unknowns, the final velocity and theta, cosine theta. So we need to use the conservation momentum along y to get two equations for two unknowns so we can solve the problem. So for y, originally we have this vehicle moving this way, so the original momentum, mass by velocity. After collision, you have the new mass, m car plus m truck, and you have v final sine theta. So now we have two equations with two unknowns, V final and theta. We can solve them simultaneously. We get for tan theta 1.33. This means theta is 53.1 degrees. So now we know what's theta. And we substitute for theta that angle and solve for V final. When we substitute the numerical values, we get 15.6 meter per second. So I hope now we have a clear understanding of conservation of momentum principle and how to apply it during collisions.